There is an object sitting at the center of our galaxy right now that will outlive everything you have ever known. It will outlive the sun. It will outlive the earth. It will outlive every star that has ever burned in the sky, every constellation humanity has named, every galaxy we have photographed, every solar system that has ever harbored warmth or light or possibility. Long after the last star collapses into cold silence, this object will still be here. And it will not be alone, scattered across what remains of the universe, in a darkness so complete that the word darkness itself becomes inadequate. Black holes will endure. Not thousands of them, not millions, but a number so vast it would take longer to count than the current age of the universe has existed. They will float through empty space, unhurried, patient, in a way that no human concept of patience can adequately describe. But even black holes are not eternal. Even they will end, and when the very last black hole in the universe finally disappears, not in an explosion, not in a catastrophe, but in something far stranger, far quieter, something truly unprecedented will happen. For the first time in the history of the cosmos, there will be nothing left that curves space-time, nothing left that traps light, nothing left that holds the memory of the stars that made it. The universe will be empty in a way it has never been empty before. Tonight, we are going to follow the entire journey, from the black holes that exist right now, burning at the hearts of galaxies, to the last one standing at the very end of time, and to the quiet, almost impossibly strange way it finally lets go. But to understand how black holes end, we first have to understand something that most people don't realize they've been getting wrong their whole lives. We have to understand what a black hole actually is. Most people carry a mental image of a black hole as something like a cosmic drain, a hole in space that pulls everything toward it, hungry and endless, consuming whatever drifts too close. It is a dramatic image, and it is not entirely wrong. But it is incomplete in a way that matters enormously for everything that follows. A black hole is not a hole. It is not empty space, and it is not an absence of matter. It is, in fact, one of the densest concentrations of matter that the universe permits. When a massive star exhausts the nuclear fuel that has kept it burning for millions or billions of years, the outward pressure that once held it open against the crushing weight of its own gravity suddenly disappears. What happens next occurs in a fraction of a second. The outer layers collapse inward with terrifying speed, and the core, depending on how massive the star was, either becomes a neutron star or something else entirely. When the core mass is large enough, nothing stops the collapse. Not the pressure of electrons pushing against each other. Not the pressure of neutrons, packed so tightly they resist further compression. The collapse continues past every known threshold until the matter is compressed into a region of space so small that our current mathematics breaks down trying to describe it. We call that region a singularity, though the word is really a confession of ignorance. It is where the equations stop working rather than where we genuinely understand what exists. Around that singularity is a boundary, not a physical surface, not a wall or a membrane you could touch, but a point of no return in spacetime itself. A threshold beyond which the geometry of space and time becomes so distorted that all paths, every possible trajectory anything could take, lead inward. That boundary is the event horizon. The event horizon is the true definition of a black hole. It is not the singularity at the center. It is that invisible sphere of no return. And because nothing that crosses it can ever come back. Not matter, not light, not information of any kind. The interior is permanently cut off from the rest of the universe. So from outside, a black hole looks like a region of absolute darkness. Not because it emits no light, but because no light can escape from within it. Any photon that crosses the horizon is simply gone from the perspective of the universe outside. This is already strange enough, but the story gets stranger because black holes are not all the same. There are stellar mass black holes, formed from the collapse of individual stars, typically containing between a few and perhaps 100 times the mass of our Sun. These are the most common kind, scattered throughout galaxies in numbers that likely reach into the billions for a galaxy the size of the Milky Way alone. Then there are intermediate mass black holes, a category whose existence was debated for decades and is still only confirmed in a handful of cases. Sitting somewhere between hundreds and hundreds of thousands of solar masses, their origin is still not fully understood. They may form through the merging of smaller black holes. They may form through some other process that we haven't fully worked out yet. And then there are the supermassive black holes. These are the ones that sit at the centers of galaxies. Not just some galaxies. Nearly every large galaxy we have examined closely appears to contain one. The Milky Way's central black hole, named Sagittarius A, contains approximately 4 million times the mass of the Sun. In neighboring galaxy M87, the black hole is far larger, around 6.5 billion solar masses. In some of the most extreme cases, black holes have been found containing tens of billions of solar masses, objects so enormous that if you placed one where our Sun is, its event horizon would extend far beyond the orbit of the outer planets. How supermassive black holes grew so large remains one of the most actively debated questions in modern astrophysics. We have found them already fully formed when the universe was less than 1 billion years old, a tiny fraction of its current age. How they reached such extreme sizes so quickly is a puzzle that cosmologists are still working to unravel. But understanding black holes is really only the beginning of what we need to know, because the question this documentary is built around is not merely what black holes are. The question is what happens to them when the rest of the universe is gone. And to understand that, we need to follow the universe itself as it ages. The universe today is roughly 13.8 billion years old. That sounds ancient, and by any human standard it is. But measured against the timescales that matter for this story, the universe we inhabit is extraordinarily young. We are living, in a very real sense, in the golden age of stars. Right now, across hundreds of billions of galaxies, stars are forming. Clouds of hydrogen and helium are collapsing under their own gravity, growing dense and hot enough to ignite nuclear fusion in their cores. Existing stars are burning through their fuel, expanding into giants, exploding as supernovae, scattering heavy elements into the interstellar medium. New solar systems are forming. Somewhere in that vast cosmic activity, the conditions for chemistry and biology that eventually produce curious minds like ours are arising and perhaps ending and arising again. But this age will not last. Cosmologists have mapped out the deep future of the universe in broad strokes, and what they find is a story of increasing quietude. The universe's star formation rate, the amount of new stellar material being converted into burning stars per year across all of creation, has already been declining for billions of years. It peaked somewhere around 10 to 11 billion years ago, in an era called cosmic noon, when galaxies were young and crowded with gas and churning out new stars at a rate that dwarfs anything happening today. Since then, the rate has been falling, slowly but continuously. The gas that stars need to form is being used up, and what remains is not always in the right conditions to collapse. Over the next tens of billions of years, star formation will continue, but at an ever-declining pace until, eventually, in an era that astronomers call the degenerate era, and that won't begin for something like 100 trillion years from now. The last star will flicker on, burn for a while, and go out. 100 trillion years. The number is almost meaningless without context. Our current universe is 13.8 billion years old. 100 trillion years is more than 7,000 times longer than the universe has already existed. In that span of time, the cosmos will change in ways that make our current universe look like a first draft. The stars we see tonight, Sirius, Betelgeuse, Vega, the faint smear of the Milky Way, will all be gone. The constellations they form, already slowly shifting over thousands of years, as each star moves along its own path through the galaxy, will dissolve completely. The Sun will have expanded into a red giant, and then collapsed into a cooling white dwarf. Earth, if it still exists at all, will be a scorched remnant orbiting a dim, fading ember. And when that last star goes dark, what is left? Not nothing, not yet. What remains is an assortment of stellar remnants. White dwarfs slowly cooling over inconceivable timescales, neutron stars spinning down across billions of years, perhaps rogue planets wandering through the void between former galaxies, and the black holes. The black holes will still be there. They will have been accumulating for the entire history of the universe, and they will continue to exist long after the last star has died. And this is where the story truly begins. Because what happens to a universe that contains only black holes and cold, stellar remnants and the slowly spreading emptiness of dark energy? What happens in the age of black holes? Imagine the universe 100 trillion years from now, the sky, if you could survive long enough to observe it, and if there were any atmosphere left anywhere to cast sunsets of a sky, would be unlike anything we can genuinely conceive of today. The galaxies that now populate the night with their faint, fuzzy light have long since merged, collided, and restructured themselves into enormous elliptical shapes that have gradually spread their stars into vast, tenuous halos. The individual stars within them are cooling white dwarfs by now, dim and fading, each one carrying the last warmth of nuclear fires that burned out long ago. Over timescales stretching into the quadrillions of years, numbers with 15 or 16 zeros. Even these remnants will undergo changes. Brown dwarfs, those failed stars too small to ever ignite fusion, will occasionally wander close to each other and merge, briefly reigniting as red dwarfs before fading again. White dwarfs will cool so slowly that even in this unimaginably distant era, some of them are still technically warm, though barely. The black holes, in contrast, are essentially unchanged. A black hole formed from the collapse of a stellar core 5 billion years ago looks, from the outside, almost identical to one formed 500 trillion years ago. This is one of the profound and strange properties of black holes. They have no surface texture. They have no composition in the ordinary sense. They are characterized entirely by three properties: their mass, their rotation, and their electrical charge, and nothing else. No record of what fell into them. no memory of the star that made them, no trace of the atoms that were compressed beyond the horizon. This property is sometimes called the no-hair theorem, a whimsical name given by the physicist John Wheeler, who is credited with popularizing the very term black hole. The idea is that black holes are bald, featureless, with no individual characteristics beyond those three numbers. Two black holes with identical mass, rotation, and charge are indistinguishable from each other, even if one formed from the collapse of a hydrogen gas cloud and the other from the collision of 100 smaller black holes. In the age of black holes, this becomes the dominant feature of the universe. Simplicity, vastness, emptiness, punctuated by these dense, featureless objects drifting apart as the expansion of space continues to push everything away from everything else. The supermassive black holes at the centers of what were once galaxies are still there. They have grown over the eons by consuming gas, dust, stars, stellar remnants, and occasionally each other. The black hole at the center of what was the Milky Way, still 4 million solar masses when our sun burned bright, may have grown considerably larger by now through the slow merger of galactic remnants. In some parts of what was the universe's largest galaxy clusters, supermassive black holes of unimaginable size may have formed through the mergers of the supermassive black holes of hundreds of individual galaxies. And yet, even these colossal objects, even black holes containing billions or trillions of solar masses, are not permanent. Something is happening to them, something that, when it was first proposed, seemed almost too strange to be real. Something that Stephen Hawking spent years of his life working to understand. And that transformed our entire conception of what black holes truly are. In 1974, Stephen Hawking published a paper that shocked physicists. The paper was titled Black Hole Explosions, and in it, Hawking made a claim that seemed, at first glance, to directly contradict everything that had been established about black holes. He claimed that black holes are not, in fact, completely black. They glow, they emit radiation, they slowly, almost impossibly slowly, lose mass, and they will eventually evaporate entirely. The mechanism Hawking described has become known as Hawking radiation, and understanding it requires a brief but important detour into the nature of empty space itself. In classical physics, the physics of Newton, of everyday intuition, empty space is simply empty. A vacuum contains nothing. But in quantum mechanics, the picture is radically different. The vacuum is not empty. It is a seething, fluctuating sea of virtual particles. Pairs of matter and antimatter particles that constantly appear from the vacuum, exist for a brief moment, and then annihilate each other and return their borrowed energy to the void. This is not a metaphor or a mathematical convenience. The effects of these virtual particles are measurable in laboratory experiments, and they are real. Now consider what happens at the event horizon of a black hole. A pair of virtual particles appears, as such pairs do everywhere in space. At every moment, normally they annihilate each other almost immediately. But at the event horizon, something different can happen. One of the particles can fall across the horizon into the black hole, while the other escapes into the universe outside. When this happens, the particle that escapes cannot annihilate with its partner. The partner is gone, beyond the horizon, permanently separated from it. The escaping particle becomes real. It carries energy into the universe outside the black hole. Where does that energy come from? It comes, in a sense, from the black hole itself. The black hole's mass decreases slightly every time this happens. Effectively, the black hole is radiating energy away, particle by particle. Hawking radiation is extraordinarily feeble for any black hole of significant size. The temperature at which a black hole radiates is inversely proportional to its mass. The larger the black hole, the colder its radiation, and the more slowly it loses mass. For a stellar mass black hole, the Hawking temperature is so low and the rate of evaporation so slow that the process would take longer than the current age of the universe, raised to an enormous power, to complete any noticeable change. For a supermassive black hole, the situation is even more extreme. The supermassive black hole at the center of the Milky Way, Sagittarius A, radiates at a temperature so fantastically close to absolute zero that it defies description. In our current universe, it is actively absorbing far more energy from the cosmic microwave background radiation, the faint afterglow of the Big Bang, than it could ever lose through Hawking radiation. But here is the crucial point. The cosmic microwave background radiation is not constant. As the universe expands, the background radiation gets progressively cooler. Eventually, in a very, very distant future, the temperature of the cosmic microwave background will fall below even the Hawking temperature of the largest black holes. At that point, black holes will begin to radiate away energy faster than they absorb it. They will begin to evaporate. And nothing, not mass, not rotation, not any property a black hole possesses, can prevent this from eventually happening. The question is only, how long will it take, and which black hole will be the last one standing? Before we follow the last black hole to its final moments, we need to reckon honestly with the numbers involved. And this is where the story becomes genuinely difficult for the human mind to grasp. Not because the concepts are complex, but because the scales involved are so far outside anything evolution equipped us to intuit. The evaporation time of a black hole through Hawking radiation scales with the cube of its mass. This means that a black hole 10 times more massive than another takes 1,000 times longer to evaporate. A black hole 100 times more massive takes 1,000,000 times longer. The relationship is brutally steep. Adding mass doesn't add evaporation time linearly. It multiplies it. For a black hole with the mass of our Sun, which is not a particularly massive stellar mass black hole, but a useful reference point, the evaporation time has been calculated at roughly 2 times 10 to the power of 67 years. That is a 2 followed by 67 zeros. The current age of the universe is approximately 14 billion years, or about 10 to the power of 10 years. The evaporation time of a solar mass black hole is therefore longer than the age of the universe, by a factor that itself has more zeros than any number we commonly use in everyday life. But stellar mass black holes are small by the standards of what exists in the universe. A supermassive black hole containing 1 billion solar masses would take on the order of 10 to the power of 83 years to evaporate through Hawking radiation. That is a number so large that every atom in the observable universe could be used as a digit, and there still would not be enough to write it out in full. And the most massive black holes we have observed, those containing tens of billions of solar masses, push the calculation further still into timescales that require new ways of thinking about what numbers even mean in a practical sense. For context, the Stelliferous era, the era of stars, spans from the Big Bang to roughly 100 trillion years, 10 to the power of 14. The The degenerate era that follows spans from there to about 10 to the power of 40 years, during which white dwarfs cool and protons may or may not decay. The black hole era begins after that, stretching from 10 to the power of 40 years to somewhere around 10 to the power of 90 or 100 years, when the last black holes finally finish evaporating. The black hole era is not a brief interlude. It is, by far, the longest era the universe will experience. Everything we know, the Big Bang, the formation of galaxies, the evolution of stars, the existence of life, the rise of any civilization anywhere in the cosmos, fits into a tiny sliver at the very beginning of what will eventually be the universe's total history. And during the black hole era, what is the universe actually doing? For most of it, almost nothing that would register on any scale we currently use. The black holes drift apart slowly as the expansion of space continues. There are no stars to provide light. There is no gas to form new stars. There may be occasional collisions or mergers between black holes. Gravity, after all, still operates even in the cold dark. But these events become progressively rarer as the distances between objects grow. The cosmic microwave background continues to cool, its wavelengths stretching with the expansion of space, its photons growing ever more faint and ever more widely separated. At some point in this vast, dark future, the temperature of the background radiation will fall to levels so extraordinarily low that the coldest stellar mass black holes, those with the highest Hawking temperatures because they are smallest, will begin to radiate net energy into their surroundings for the first time. They will begin to glow in a sense that no conventional telescope could ever detect, radiating in wavelengths longer than anything we observe today. At temperatures a billionth or a trillionth of a degree above absolute zero, and slowly across timescales that dwarf the current age of the universe by incomprehensible factors. They will shrink. The smallest black holes die first. This might seem counterintuitive. We might expect that the ferocity of a small black hole's evaporation, the higher temperature of its Hawking radiation, would make it feel dangerous, energetic, notable, but on we are considering. Even the smallest stellar mass black holes take an almost incomprehensibly long time to evaporate. Nevertheless, they go first. As a black hole loses mass through Hawking radiation, something important happens. Its temperature goes up. The relationship between mass and Hawking temperature is inverse. As the mass decreases, the temperature increases. This creates a feedback effect. As the black hole shrinks, it gets hotter. As it gets hotter, it radiates more intensely. As it radiates more intensely, it loses mass faster. As it loses mass faster, it gets hotter still. This runaway process is not immediately dramatic. For most of the evaporation lifetime of a stellar mass black hole, the process is glacially slow, barely detectable, even in principle. The black hole spends the vast majority of its lifespan losing mass at an almost imperceptibly slow rate, maintaining a temperature barely above absolute zero, radiating only the faintest possible whisper of energy into the surrounding universe. But at the very end, in the last tiny fraction of a second before complete evaporation, the process suddenly accelerates beyond anything that precedes it. As the mass falls below a certain threshold, the temperature spikes dramatically. The black hole, now reduced to something with perhaps only a few times the Planck mass remaining, suddenly blazes with energy far exceeding anything in its billions or trillions of years of prior existence. What happens in these final moments depends on physics we do not yet fully understand. Specifically, the physics that operates at the intersection of quantum mechanics and gravity, a regime we have no confirmed theory to describe. Does the black hole evaporate completely to nothing? Does it leave behind a stable Planck mass remnant? A kind of fossil, a final relic encoding some record of what once fell in? Does information escape in the final burst of radiation, resolving in the last moment what physicists call the black hole information paradox? The honest answer is that we do not know. The mathematics of Hawking's calculation breaks down precisely when it would need to describe the final moments. General relativity and quantum mechanics, our two greatest physical theories, are still not reconciled with each other, and it is in the final evaporation of a black hole where that incompleteness becomes most acute. What we can say with greater confidence is that the energy released in the final stages of evaporation is significant. The last fractions of a second of a black hole's life produce a burst of radiation, potentially gamma rays and other high-energy particles, that would be detectable, in principle, from some distance in an otherwise dark universe. In the black hole era, these bursts would be among the only events occurring anywhere. The death of each small black hole is a flash in the dark. Not a prolonged explosion, not a catastrophe that transforms anything around it. Just a burst of energy, a final blazing moment, and then silence. A region of space that once curved light and trapped anything that strayed too close is now simply space again. Flat, uncurving, empty. And when the last stellar mass black hole has died, when the last one has completed its long, patient evaporation, the universe is a different place. The objects that remain are only the massive and the supermassive. The black holes whose longer lifetimes reflect their greater mass, which have spent the entire preceding era absorbing what little remained to absorb and growing, perhaps incrementally larger, while their smaller siblings died around them. But these survivors are not safe forever. They are simply waiting longer. There is a quality of the black hole era that deserves particular attention, because it is so alien to any experience of time that we have ever had or could have. Consider what it means for a human being to experience the passage of a year. There is summer and winter. There is the cycle of days, the rhythm of sleep and waking. There is change in weather, in the growth of plants, in the aging of faces. Time for us is marked by events, by things happening, by the world around us shifting. Now try to imagine the passage of time in a universe where almost nothing is happening. In the early black hole era, there are occasionally events. A white dwarf, cooling slowly over unimaginable timescales, finally approaches the temperature of its surroundings and fades. Two neutron stars, whose orbits have been slowly decaying over quadrillions of years due to the emission of gravitational waves, finally merge in a brief burst of energy. A rogue planet, wandering since the breakup of its solar system in the degenerate era, drifts close enough to a black hole to be captured and eventually consumed. But these events grow rarer and rarer as the era progresses. The universe continues to expand. Distances grow. The probability of any two objects encountering each other falls, and eventually the universe reaches a state that some cosmologists have called the heat death. Not literally hot, but thermodynamically equilibrated in the sense that the kind of energy gradients that allow events to happen have largely smoothed out. In the heat death, almost nothing occurs on any timescale relevant to human experience. The black holes drift through a universe that is, for all practical purposes, featureless. They are separated by distances so large that even light, traveling at the cosmic speed limit, would take longer to bridge the gap than many of the processes we have already described. They are, in a sense, already alone, and yet they continue to evaporate. Hawking radiation does not require company. It does not require a background of events or a surrounding medium. It is a process intrinsic to the black hole itself, arising from the geometry of its event horizon. And it continues, regardless of how empty and cold the universe around it has become. Each black hole is on its own clock, ticking down at a rate determined by its mass, losing energy particle by particle, or rather, losing energy in the form of radiation that drains away across the surrounding darkness. The intermediate mass black holes, those between stellar and supermassive in size, evaporate next. Then comes the long dominion of the supermassive black holes, the objects that once anchored galaxies, and that now float through a universe without galaxies, growing ever so slightly colder as their mass diminishes over eons, that make the stelliferous era look like a passing thought. And through all of this, a question hangs over the entire process. Which black hole will be the last? To understand which black hole survives longest, we need to think carefully about which ones have had the opportunity to grow the largest. The supermassive black holes at the centers of galaxies are the obvious candidates. But they are not all equal. Some galaxies are larger than others. Some reside in denser environments, where mergers are more frequent and more material is available for accretion. Some have been actively feeding, surrounded by the bright disks of infalling gas that we observe as quasars, while others have grown quiescent in galaxy clusters, the largest gravitationally bound structures in the universe. The eventual merging of entire galaxies will, over cosmic timescales, bring their central black holes together. Black hole mergers are not instantaneous. Two supermassive black holes that find themselves in the same merged galaxy spend an extraordinarily long time spiraling toward each other. First, losing orbital energy through gravitational interactions with surrounding stars, and then, as they draw closer, through the emission of gravitational waves. But eventually they merge, producing a single larger black hole. Over the long history of galaxy cluster evolution, this process repeats many times. The result in the deepest future of the universe is an increasingly small number of increasingly massive black holes. The most massive black holes that have been observationally confirmed in the current universe already approach scales of tens of billions of solar masses. But in a future universe, where cluster mergers have had time to accumulate, and where the competing process of Hawking evaporation has not yet made significant inroads on objects this massive, the most massive survivors could potentially exceed even these values. There is also the question of what happens to the smaller black holes as the universe ages. A black hole, however massive it is subject to Hawking evaporation, but it is also, in principle, subject to growth if it can accrete matter. In the very early black hole era, there may still be some residual material, cold gas, rogue planets, stellar remnants, that can fall into black holes and add incrementally to their mass. However, as the universe expands and cools, and as dark energy continues to push the remaining material apart, the accretion rate drops towards zero. Black holes that are currently growing through the absorption of infalling matter, will eventually find themselves in a universe too cold and too empty to provide further sustenance. At that point, they stop growing, and Hawking evaporation, however slow, begins to dominate. The largest black holes, those that have had the most time to grow in the richest environments, will be the last survivors simply because their greater mass corresponds to lower Hawking temperatures and therefore longer evaporation timescales. Mass buys time. And in this final era of the universe, time is the only currency that matters. We have been speaking abstractly about Hawking evaporation as a slow draining of mass, but it is worth pausing to appreciate what this process actually looks like. If we could somehow observe it, the Hawking radiation emitted by a large black hole has a characteristic spectrum. It is thermal radiation, meaning it has a specific distribution of wavelengths, determined entirely by the black hole's temperature. For a supermassive black hole, this temperature is so extraordinarily low that the dominant wavelengths of emitted radiation are longer than anything we currently observe. Longer even than the longest radio waves we detect with our most sensitive instruments. As the black hole slowly shrinks over quadrillions and quintillions of years, its temperature gradually rises. The wavelengths of its emitted radiation shift slowly, growing shorter as the temperature climbs. The intensity of the radiation increases, though still at levels utterly below anything we could currently detect. From the outside, a black hole in the middle stages of its evaporations would appear as a very faint source of radiation, slowly brightening over unimaginable timescales, its spectrum shifting from the extreme far infrared and microwave into shorter wavelengths as the years accumulate. For most of its lifetime, the changes are imperceptibly gradual. The event, on the boundary of no return, slowly contracts. The diameter of the black hole decreases, but these changes, measured in the early stages, are minuscule to the point of practical invisibility. Then something changes in the final stages, as the black hole's mass falls below a certain threshold. Perhaps in the range of a few Planck masses, at scales far smaller than any elementary particle we know. The evaporation accelerates dramatically. The black hole enters a runaway regime. Its temperature shoots upward. It begins to radiate intensely across the electromagnetic spectrum, emitting photons of higher and higher energy. In the black hole era, this final burst would be extraordinary, not because of its absolute energy. Even the most energetic final evaporation of a large black hole releases far less energy than a supernova, but because of its contrast with the surrounding darkness. In a universe that contains no stars, no galaxies, no sources of light of any kind, except the slow drift of Hawking radiation from the remaining black holes, the final evaporation of a single black hole would be a genuine cosmic event, a flash. A brief, brilliant burst of energy across a wide range of wavelengths, and then nothing. The space where the black hole existed is now simply space. The gravity that once bent light around it is gone. The event horizon, that boundary that separated the interior of the universe from the rest, has closed. Whatever was inside is now gone in a form we cannot yet fully predict. And somewhere else in the vast, dark universe, the remaining black holes continue their patient evaporation, unaffected, unchanged, simply waiting for their own moment. Before we reach the final black hole, there is a question we have been circling that deserves a direct confrontation. It is arguably the deepest unsolved problem in fundamental physics, and it becomes most acute precisely at the moment we are most interested in, when a black hole finally evaporates completely. The question is this: what happens to information? In physics, information is not merely data in the casual sense. It refers to the precise quantum state of every particle, every property, every configuration, every correlation between particles that determines the history of a physical system. The laws of physics, as we understand them, are, at a fundamental level, information-preserving. Given the complete quantum state of a system at one moment, the equations of quantum mechanics allow you to calculate its state at any earlier or later time. Information is never created or destroyed. It is only transformed. Now consider what happens when matter falls into a black hole. The matter carries information, the quantum states of every particle that comprises it. But when it crosses the event horizon, it is gone. From the perspective of the universe outside, the information is seemingly trapped inside the black hole, inaccessible to anything outside the horizon. This alone is not necessarily a problem. Perhaps the information still exists, just hidden inside the horizon. But now add Hawking radiation. The Hawking radiation emitted by a black hole appears to be purely thermal. It carries no information. It is random. It does not encode anything about what fell in. So when the black hole evaporates completely through Hawking radiation, the information about everything that ever fell into it appears to simply vanish. This is a profound problem. It would mean that a fundamental law of physics, the conservation of information, is violated. Quantum mechanics and general relativity seem to be in direct conflict over this question. This conflict is called the black hole information paradox, and it was recognized by Hawking himself and has been debated by theoretical physicists for decades. There are several possible resolutions. One possibility is that the information is indeed carried out in the Hawking radiation, encoded in subtle correlations between particles that make the radiation appear thermal, but are not actually random at the quantum level. This is the position that most contemporary theoretical physicists have moved toward, supported in particular by arguments from the field of string theory, and by work on a conjecture called the holographic principle, which suggests that all the information about what is inside a volume of space is somehow encoded on the boundary of that volume. The argument that information must escape was significantly advanced in 2019 when researchers working on a calculation using techniques from the holographic principle found what they believed to be evidence that Hawking radiation does eventually carry out the information in an encoded form, not smoothly throughout the evaporation, but in a way that becomes accessible only in the final stages. This work drew on methods first suggested by physicist Don Page, who in the 1990s calculated the theoretical moment at which information would need to start leaking out if the paradox were to be resolved. A point now called the Page time. Another possibility is that the information is preserved in a stable Planck-scale remnant, a tiny object left over at the end of evaporation, too small for Hawking's original calculation to describe, which carries all the information encoded in what fell in. This resolution has fallen somewhat out of favor, partly because it leads to other theoretical problems, but it has not been definitively ruled out. A third, more radical possibility, that information is genuinely destroyed, that Hawking was right the first time, and that this represents a real modification of quantum mechanics, is taken seriously by a minority of physicists including Hawking himself in various stages of his career. For our story, this question matters because it concerns what the very last black hole takes with it when it finally evaporates. If information escapes in the Hawking radiation, then everything that ever fell into every black hole across the entire history of the universe has been, in some encoded form, leaking back out into the universe over the eons. The very last black hole, in its final evaporation, would release the last of that encoded information. The final message written in the structure of thermal radiation, unreadably complex, carrying the quantum fingerprint of everything, from the first stars to the last stellar remnants that fell in across the incomprehensible span of its lifetime. If information is truly lost, if the black hole carries its secrets into oblivion, then the last black hole's evaporation is a final, definitive erasure. The universe forgets. Whatever fell in, whatever it was, is gone not merely in the sense of being transformed, but in the sense of being genuinely unrecoverable. Either way, the final evaporation of the last black hole is not merely a physical event. It is, in a deep sense, an event about memory, about what the universe keeps and what it loses. So who survives longest? We cannot, with our current understanding, name the specific black hole that will be the last to evaporate. We do not know with precision which black holes have already formed or will form, how much they will grow through accretion and mergers, or how the interplay between expansion and structure formation will ultimately determine the upper end of the black hole mass distribution. But we can reason about what kind of object the last black hole is likely to be. It will almost certainly be a supermassive black hole. More specifically, it will be among the most massive black holes that ever existed in the universe. Given that the evaporation timescale scales with the cube of the mass, even a factor of 2 difference in mass translates to an 8-fold difference in evaporation lifetime. The object with even a small mass advantage over its competitors survives not just longer, but enormously longer. The most massive black holes currently known are found in a small number of exceptional galaxies. Objects like Theon 618, a quasar, whose central black hole has been estimated at around 66 billion solar masses, or Holm 15A, at the center of a massive galaxy cluster, estimated at around 40 billion solar masses. These are extraordinary objects by any measure, and they exist in environments, the cores of massive galaxy clusters, where mergers and accretion have conspired to build up exceptional concentrations of mass. In the deep future, as galaxy clusters eventually merge on scales of tens or hundreds of billions of years, the most massive black holes in the universe may grow even larger through the merging of systems like these. The process would be extraordinarily slow. The spiral in of 2 supermassive black holes at galaxy cluster scales might take billions of years on its own, but it would be decisive. Each merger produces a larger survivor, and the largest survivors live longest. It is also worth noting that the universe extends far beyond what we can currently observe. The observable universe is limited by the distance light has had time to travel since the Big Bang, roughly 46 billion light-years in every direction. Beyond that horizon, space continues, and almost certainly contains structures, galaxies, and black holes we can never directly observe. If the observable universe is in any sense a typical sample of what exists, the universe beyond the horizon contains black holes comparable in mass to the most extreme we have found. If the universe extends much further still, and particularly if its geometry is such that it extends infinitely, then statistical reasoning alone suggests that somewhere out there are black holes even more massive than any we have observed. The last black hole in the observable universe and the last black hole in the full universe might therefore be different objects entirely. Our story, however, is necessarily constrained to what physics tells us about the kinds of objects that can exist and what their fates will be. What we can say with confidence is that the last black hole will be massive, extraordinarily massive, perhaps trillions of times more massive than the Sun, perhaps more, and its evaporation lifetime will be, accordingly, a number with so many zeros that no notation system we currently use can express it in an intuitively meaningful way. But it will end, and as it approaches its final moments, something remarkable will happen. In the deepest imaginable future, let us say we are now at a time roughly 10 to the power of 90 or 100 years since the Bang. Only the most massive black holes remain. The stellar mass black holes are long gone. They evaporated during what now seems like an almost quaint era, early in the black hole age, when the universe still contained faint wisps of their evaporation signatures. The intermediate mass black holes followed. The smaller supermassive black holes, those that anchored dwarf galaxies, those that formed in quieter environments without the benefit of major mergers. They too have long since flashed and faded. What remains is a scattered population of the most extreme objects, the survivors of billions of years of competitive accumulation, each one sitting alone in a region of space so vast that no other massive object exists within any meaningful range. They are utterly isolated, each the last remnant of what was once a galaxy or a galaxy cluster, still carrying the mass of billions or trillions of stars in their compact, featureless forms, and each one is shrinking, slowly, excruciatingly slowly, but inexorably. The Hawking radiation of an object this massive is still at an almost inconceivably low temperature, far colder than the coldest point in the current universe. But the cosmic microwave background has long since cooled below even that level. The ambient radiation field of the universe is by now essentially zero. There is nothing flowing in to compete with what is flowing out. Every particle that Hawking radiation drains from the black hole represents a tiny step forward on the evaporation clock, and as the mass slowly decreases, taking in some cases tens of additional powers of 10 of years, the Hawking temperature gradually rises. The radiation emitted shifts to slightly shorter wavelengths, slightly higher energies. The rate of mass loss, still unimaginably slow, begins to creep upward. An outside observer watching this process, if any observer of any kind could survive to witness it, which is another problem entirely, would see the black hole growing almost imperceptibly warmer over spans of time that transcend any ordinary sense of duration. Then, in the final stages, the acceleration. The mass falls toward the critical threshold. The temperature rises not linearly, but exponentially, relative to the mass remaining. The radiation brightens, and in the very final fraction of a second, in a burst of energy that, for all its absolute smallness relative to cosmic standards, is the most significant event occurring anywhere in the universe at that moment, the last massive black hole completes its evaporation. The event horizon contracts, and closes. The final second of a black hole's existence is unlike every other second that preceded it. for most of its life. Whether that life lasted a few quadrillion years or a number so large that it requires its own mathematical notation. The black hole was defined by stillness, not in the sense of being motionless, but in the sense of being fundamentally unchanged by the passage of time. It accumulated mass here, lost a negligible fraction through Hawking radiation there, and perhaps merged with another black hole in a brief gravitational embrace that, for all its violence, left it essentially the same kind of object it had always been. But in the final moments, all of that patience collapses into something explosive. The physics of the very last stages of black hole evaporation is one of the genuine frontiers of theoretical physics. What we know with confidence comes from Hawking's original calculation, which describes the process beautifully for most of a black hole's lifetime, but breaks down as the mass approaches what physicists call the Planck mass. Approximately 22 micrograms, a quantity so small it contains fewer atoms than a typical bacterium. When the black hole shrinks to this scale, the wavelength of its Hawking radiation becomes comparable to the size of the black hole itself, and the semi-classical approximation that Hawking used, essentially treating the black hole as a fixed background geometry on which quantum fields fluctuate, is no longer valid. What replaces it is unknown, because the physics required to describe it is the quantum theory of gravity, and that theory does not yet fully exist. What we can say is this: in the final moments, the black hole is no longer cold. It is extraordinarily hot by any ordinary standard. A black hole in its terminal phase, with only a few Planck masses remaining, radiates at temperatures approaching or exceeding the Planck temperature, the highest temperature that the framework of physics permits us to assign a meaning to. At these temperatures, the radiation is not merely photons and ordinary particles. It is a burst of everything: photons, electron-positron pairs, quarks, quark-gluons, and potentially exotic particles we have not yet discovered, all streaming outward in a concentrated blast. The total energy released in this final burst is modest in cosmic terms. Even a black hole that began its life with 1 billion solar masses and has been slowly losing mass for an incomprehensible span of time, arrives at its final Planck mass stage, having already radiated away the overwhelming majority of its energy. The last burst is the final exhale of a process that has been running longer than anything else in the history of the universe. But in a universe that contains almost nothing else. No stars, no galaxies, no sources of energy of any kind. Even this modest burst is significant simply because it is something. It is an event in a cosmos that has long since ceased to have events of any kind. For the last black hole, that final burst is the last event. After it, there are no more events. There is, as far as physics currently tells us, simply the expanding, cooling, empty geometry of space-time. Uninterrupted, without structure, without gradient, without any process that can produce change of any kind. The universe continues to exist, in the sense that space-time continues to expand. But nothing in it happens. Try to hold in your mind a universe that is genuinely, completely empty of any organized structure. Not the empty space between galaxies that we know today, which is still threaded with dark matter and crossed occasionally by rogue photons and cosmic rays. Not the empty space of the far future that still contains cooling stellar remnants and drifting black holes. But a universe in which every particle of ordinary matter that still exists is either in the form of electrons and positrons slowly drifting apart in the expanding void, or in the form of photons with wavelengths so long they carry essentially no energy, redshifted almost entirely out of existence by the expansion of space. This is the universe after the last black hole evaporates. Physicists call this state the dark era, or sometimes the far future era, and it is in some ways the most alien phase the universe will ever experience. There are no sources of energy. There is no chemical complexity. If protons are unstable, if the proton decay that grand unified theories predict but that has not yet been experimentally confirmed occurs on the timescales that some theories suggest, then even the protons in the last remaining particles of ordinary matter will have long since decayed, leaving only electrons, positrons, neutrinos, and photons. Dark energy, the mysterious force responsible for the accelerating expansion of the universe we observe today, will presumably still be present. Space will continue to expand, but expansion in the absence of any matter or radiation with which to interact is a purely geometric process. It changes the scale of space, but with nothing in that space to be affected, it carries no observable consequences. What does this universe look like from the inside? This is a question that almost defies meaningful engagement, because looking requires light, and light requires energy, and energy in organized forms is precisely what this universe no longer has. If we imagine some hypothetical observer, some form of awareness we cannot physically construct, but can in principle imagine, floating in this universe, they would perceive absolute darkness. Not the darkness of a room with the lights off, not the darkness of deep space, but a darkness more complete than any we can experience, a darkness that contains no photons at all, above a certain infinitesimal energy, no sources of any kind, nothing for any sensory apparatus to detect. The temperature of this universe is extraordinarily close to absolute zero, but not quite there. Dark energy, operating in a universe that has reached this state, may set a minimum temperature floor, below which the universe cannot cool, sometimes called the de Sitter temperature, which is incomprehensibly small but not zero. In this sense, the universe never quite reaches absolute zero. It asymptotically approaches it, never fully arriving. And in this state, something remarkable and deeply strange is true. The universe is, in the most technical sense, in thermodynamic equilibrium. The gradients that allow work to be done, that allow organized processes of any kind to occur, are gone. There is no meaningful difference between one region of space and another. No concentration of energy, no temperature difference, no chemical potential. The universe has reached what physicists call maximum entropy. Entropy is a measure of disorder, or more precisely, of the number of possible microscopic arrangements of a system that correspond to the same macroscopic state. The more arrangements correspond to a state, the higher its entropy. A universe in maximum entropy is one in which the macroscopic state is compatible with the maximum possible number of microscopic arrangements, which is another way of saying that the macroscopic state carries no useful information about the specific microscopic arrangement of anything. This is the heat death of the universe, predicted in the 19th century by physicists reasoning from the second law of thermodynamics, and now confirmed in its broad outlines by what we understand about the future of the cosmos. It is not a dramatic death. There is no explosion, no collapse, no catastrophic event. It is a death of exhaustion, a universe that spent all of its usable energy and settled into a state of perfect, unchanging, featureless equilibrium. We have been narrating the end of the universe with a confidence that deserves a moment of honest examination. The broad outline of what we have described. The stellar era giving way to the degenerate era, then the black hole era, then the final evaporation of black holes through Hawking radiation, and finally the dark era, is based on our best current physical theories. And those theories are extraordinarily well tested in the regimes where we can check them. But the story we are telling extends into domains where no experimental test is currently possible, and where our theories make assumptions that may not hold. Consider proton decay. Several prominent grand unified theories, attempts to extend the standard model of particle physics into a more complete framework that unifies the strong, weak, and electromagnetic forces, predict that the proton is not truly stable. They predict that protons will eventually decay into lighter particles, with half-lives that current experiments constrain to be at least around 10 to the power of 34 years or longer. No experiment has yet detected a proton decay event, but if protons do decay, then the stellar remnants, white dwarfs and neutron stars, that persist through the degenerate era will gradually disintegrate, changing the nature of that era significantly. The mass of the proton decay products would not disappear. Energy is conserved, but the organized structures, the compact remnants of stars, would dissolve, leaving only the decay products and the black holes as the organized objects of that era. The details of proton decay, or its possible absence, affect the precise timeline of the degenerate era, but do not fundamentally alter the black hole era that follows, since black holes do not contain protons in any conventional sense. Then there is the question of dark energy. Dark energy, the name we give to whatever is causing the expansion of the universe to accelerate, is currently characterized by what is called a cosmological constant, a fixed energy density of empty space that remains constant as the universe expands. If dark energy truly is a cosmological constant, the universe will expand forever at an accelerating rate, and the future we have described unfolds more or less as painted. But some theoretical models suggest that dark energy might not be constant. It could vary with time, and in certain models, sometimes called phantom energy models, dark energy could grow stronger as the universe ages, eventually becoming so dominant that it tears apart not just galaxies and then solar systems, but eventually atoms, and then subatomic particles, in a catastrophic event called the Big Rip. If the Big Rip occurs, the timeline we have been describing is cut short. Black holes themselves would not survive. The phantom energy would eventually overcome even the gravity of a black hole's event horizon, tearing the black hole apart before it could complete its Hawking evaporation. Current observations suggest that dark energy behaves very much like a cosmological constant, and the Big Rip scenario is not currently favored by the data, but it has not been definitively ruled out. There is also the possibility, raised by quantum field theory in curved spacetime, that the universe, even in its lowest energy state, may not be truly stable. The Higgs field, which gives elementary particles their masses, may be in a metastable state, what physicists call a false vacuum. If this is the case, then quantum tunneling could trigger a phase transition in which the Higgs field collapses to a lower energy true vacuum, creating a bubble of different physics that expands at the speed of light, obliterating everything it passes through. Current measurements of the Higgs boson mass and the top quark mass suggest that the universe may indeed be in a metastable state, though the lifetime of the false vacuum, if this interpretation is correct, is so long as to be effectively astronomical, even by the standards of the timescales we have been discussing. These uncertainties are not reasons to distrust the overall picture. They are honest reflections of what science is, an ongoing process of refining our understanding against the available evidence, extending our reach into domains where our theories are tested, and maintaining genuine humility about the domains where they are not. The story of the last black hole is our best current understanding of the ultimate fate of organized structure in the universe. It may require revision, but it is not arbitrary speculation. It is the logical consequence of following our best physical theories as far as they can coherently be followed. We spoke earlier about the black hole information paradox. Now, as we approach the final moments of the last black hole, the question becomes unavoidable. What happens to everything that ever fell into this object? Think about what the last supermassive black hole contains within its history. Over the course of its existence, spanning perhaps 10 to the power of 90 years or more, it has accreted enormous amounts of material. In its early life, when it sat at the center of a galaxy, it consumed gas, dust, and entire stars. As its galaxy merged with others, it absorbed other black holes, carrying within those mergers the accumulated contents of their own histories. It absorbed the remnants of stellar populations. It absorbed rogue planets and drifting chunks of material that wandered too close over the billions and trillions of years of its middle age. Within the effective information content of this black hole is the quantum state of every particle that ever crossed its horizon. Every proton, every electron, every photon that fell in across its entire history has contributed its quantum state to what, from outside the horizon, presents itself as a featureless mass with only 3 measurable properties. Where did all that information go? The answer to this question is one of the most contested in modern theoretical physics. But in recent years, a growing consensus has emerged. Not a complete proof, but a powerful suggestion from multiple converging lines of evidence. That information does escape from black holes, encoded in the quantum correlations of the Hawking radiation that the black hole emits across its lifetime. The key insight comes from work that followed from an observation by physicist Don Page in 1993. Page pointed out that if information is to be conserved, then the Hawking radiation emitted in the second half of a black hole's evaporation must be quantum mechanically entangled with the radiation emitted in the first half in a very specific way. The entropy of the emitted radiation, its apparent randomness, must eventually start to decrease, even though individual photons of Hawking radiation appear completely thermal and random. The point at which this happens, when the radiation entropy peaks and begins to decline, is called the Page time, and it occurs roughly when the black hole has lost about half its initial mass. Before the Page time, the Hawking radiation appears completely random and carries no accessible information. After the Page time, the radiation is still individually indistinguishable from thermal noise, but it is globally correlated with earlier radiation in a way that, in principle, allows the quantum state of everything that fell in to be reconstructed. In 2019, multiple research groups working independently arrived at calculations supporting this picture. using a technique called the island formula, derived from thinking about gravity from the perspective of the holographic principle, and from calculations in simplified models of quantum gravity. They found that the entropy of Hawking radiation follows exactly the curve Page predicted. It rises during the first half of the evaporation and then decreases during the second half, approaching zero as the black hole completes its evaporation. This is a remarkable result. It suggests that Hawking radiation is not truly random, that the information encoded in what fell into the black hole is not lost, but is gradually re-encoded in the quantum structure of the outgoing radiation over the course of the evaporation process. For the last black hole, this means something profound. Every particle that crossed its horizon across its entire history, across the full span of the black hole era, has been leaking back out, encoded in the Hawking radiation, written in correlations between photons emitted billions of years apart. The information is not readable in any practical sense. No physical instrument could reconstruct it. The correlations are spread across radiation, emitted across timescales longer than the current age of the universe. But the information is there, and in the final burst of the last black hole's evaporation, the last of it comes out. The last photons of Hawking radiation carry the last quantum correlations, the last encoding of whatever fell in across the immeasurable span of this object's existence. And then, complete, nothing remains within a horizon. Because there is no horizon, the information of the universe is now in the radiation, completely dispersed, infinitely diluted, encoded in the correlations of photons, spread across a universe that is itself expanding beyond any possibility of their ever interacting with each other again. The information exists, but it exists in a form so thoroughly scrambled, so irreversibly dispersed, that it might as well be lost for all practical purposes. The universe remembers everything, and the universe can tell you nothing. After the last black hole has evaporated, after the last burst of Hawking radiation has dispersed into the expanding dark, the question of what remains is surprisingly interesting. The most immediate answer is very little. Photons, with wavelengths so long and energies so low that they carry essentially zero energy per photon by any practical measure. These are the photons of the Hawking radiation, spread across the universe, red-shifted by the continued expansion of space to wavelengths longer than the observable universe was when they were emitted, possibly electrons and positrons. These fundamental particles, if they are truly stable, and current measurements suggest they are, with lifetimes too long to measure, will persist indefinitely. But in an expanding universe, the density of any massive particle falls as the universe grows. Electrons and positrons, already extraordinarily sparse in this distant future, become more and more isolated as space expands. The probability of two of them ever encountering each other falls asymptotically toward zero. Neutrinos, similarly, persist if they are stable, and evidence suggests they are, again, isolated, cold, expanding apart, playing no further role in any organized process. And dark matter, whatever it is, if dark matter consists of stable particles, as most models assume, those particles persist as well, spread throughout the universe, invisible, interacting with nothing. These are the final constituents of the universe. A thin, cold soup of particles, some massless like photons, some extraordinarily light like neutrinos, some of unknown character like dark matter, embedded in a geometry of space-time that continues to expand, driven by dark energy, stretching the distances between these particles toward true infinity. No structure forms, no stars condense, no organized process of any kind occurs. The second law of thermodynamics ensures this. The universe has reached its maximum entropy state, and every random fluctuation that occurs, and quantum mechanics guarantees that random fluctuations will continue to occur, immediately disperses before it can grow into anything organized. There is, however, one extraordinarily curious exception to this picture proposed by the Boltzmann brane argument. Though it is more of a philosophical puzzle than a physical prediction in any actionable sense. In a universe at maximum entropy, quantum fluctuations will, over times that make the evaporation timescale of the last black hole seem brief by comparison, occasionally produce random configurations of particles. The overwhelming majority of these fluctuations are tiny, brief, and immediately disperse. But if the universe persists for long enough, and in certain cosmological models it does, then even extremely improbable fluctuations will eventually occur. Among the most improbable, but not technically impossible fluctuations, is the spontaneous assembly, by pure quantum chance, of a configuration of particles that constitutes a functioning mind, with memories, sensory experience, and the capacity to think, that exists for a moment before dispersing back into randomness. These hypothetical entities are called Boltzmann branes, named for the 19th century physicist Ludwig Boltzmann, who grappled with similar questions about entropy and cosmology. The Boltzmann brane argument is not a prediction that such minds will commonly arise. It is more of a reductio ad absurdum that cosmologists use to test whether their theories of the universe's far future make sense. A theory that predicts Boltzmann branes should vastly outnumber ordinary observers like us is generally considered to have something wrong with it. Because our experience of being ordinary observers who evolved in a low-entropy environment is far more probable than being a Boltzmann brane, and our theories should reflect that. But the argument does illustrate something important. Even in the maximum entropy universe, the universe is not literally static. It fluctuates. Quantum mechanics ensures that it will always fluctuate at some level forever. The universe after the last black hole is not the absence of all change. It is the reduction of change to the irreducible minimum permitted by the laws of nature. That minimum turns out to be quite extraordinary to contemplate. A universe of pure quantum foam, expanding forever, fluctuating on its smallest scales, without direction, without process, without memory. This is not a question with a physical answer. Black holes do not have awareness. They do not have experience. They do not know anything in any meaningful sense. But the question itself reveals something worth exploring. A black hole is, in a fundamental sense, a local phenomenon. Its event horizon defines a region of space-time. Its gravitational influence extends outward, but weakens with distance. A supermassive black hole floating alone in the void of the late black hole era has no way, in any physical sense, of sensing whether other black holes exist elsewhere in the universe. Its evaporation proceeds according to its own local physics, entirely determined by its own mass and rotation, indifferent to what is happening billions or trillions of light years away. There is something in this that resonates with one of the deepest truths about the universe at large. The universe is, in its most fundamental structure, local Physics happens at specific places and times. Causes propagate at most at the speed of light. The enormous structures we observe, galaxies, clusters, filaments, are the result of local gravitational interactions playing out over the full history of cosmic time, not of some global orchestration. The last black hole does not know it is the last. It simply evaporates because that is what black holes do when they lose mass to Hawking radiation across sufficient time. The fact that it happens to be the last is a description from the outside, from a perspective that encompasses the entire history of the universe and notices that this particular evaporation event is followed by no others. From the inside of the evaporation, in the purely local physics of the event, it is simply another black hole completing a process that began with its formation and ends with the final burst of Hawking radiation. There is something clarifying about this. The end of the universe is not an event, in the way that a death or an explosion is an event. It is a statistical observation about the last occurrence of a recurring process. The universe does not end dramatically, with a single decisive moment. It ends the way a very long silence finally becomes permanent, not by any new event occurring, but by the recognition that nothing else is coming. We have traveled, in the course of this documentary, across a span of time that begins with the universe we currently inhabit, 13.8 billion years old, full of stars and galaxies and the restless activity of matter organizing itself against the spread of entropy, and ends in a darkness so complete and so ancient that no concept from our ordinary experience reaches it. The numbers involved are not merely large, they are large in a way that actively resists comprehension. And it is worth spending a moment appreciating what that means for how we should think about our own moment in this history. We live in the stelliferous era, the era of stars, and not just any point in it. We live very close to what cosmologists describe as cosmic noon, the period of maximum star formation, the period of greatest galactic activity. The universe is currently as rich in organized structure as it will ever be. Galaxies are actively forming stars. Chemistry is happening. Life, at least on this planet, has achieved a form of self-awareness and curiosity that allows it to construct, imperfectly but meaningfully, a picture of the full scope of what it inhabits. This is not a common state for the universe to be in. On a linear timescale, the stelliferous era represents an extraordinarily brief phase on the full timeline of the universe's existence. From the Big Bang to the last evaporating black hole, the era of stars is barely a sliver, like the first few seconds of a year that lasts for an incomprehensibly long time. We are, in a cosmological sense, extraordinarily early. The universe is young, not in the sense that it feels young to us. 13.8 billion years is longer than anything human civilization can easily relate to. But measured against the full arc of what is coming, the universe has barely begun. And yet the structures that exist right now, the atoms, the molecules, the biological complexity, the planets, the stars, are only possible in this brief early era. The later universe, for all its extraordinary duration, is far simpler. It has no chemistry in the biochemical sense, no nuclear reactions in functioning stars, no organized complexity of the kind that produces observers of any recognizable kind. If there is anywhere in the history of the universe where the conditions for understanding exist, it is here, now. In this early era of stars and galaxies and chemical richness, The universe's later epochs are long, but they are also simple and dark and without event. This does not make our moment special in any mystical sense, but it does mean something precise. The complexity required to contemplate the last black hole exists only in an era that, from the perspective of the full timeline, is astonishingly early. The understanding happens near the beginning. The events being understood happen near the end. There is a sense in which the Hawking radiation of the last black hole is not truly the last light in the universe. Light, electromagnetic radiation, continues to exist after the final evaporation. The photons that were emitted during the black hole's long evaporation still exist, red-shifted to extraordinary wavelengths, spread across the expanding universe. They are not absorbed by anything. They are not re-emitted. They simply propagate, their wavelengths stretching with the expansion of space, their energies falling towards zero as the universe grows. These photons are the last embers of everything that ever existed with organized energy. They carry within their quantum states, or rather, in the quantum correlations between them. If the information preservation picture is correct, some imprint of the entire history of the universe, every photon ever emitted by every star that ever burned, is somewhere in the expanding void, red-shifted and cold, but still propagating. Every particle of Hawking radiation from every black hole that ever evaporated is out there, spread across space. None of it can be recovered. None of it can be decoded. The correlations that would allow reconstruction of the initial state are diluted across a volume of space that grows forever. But in a purely formal, abstract sense, the information is there. The universe, in its final state, is not empty in the information theoretic sense. It is full, overwhelmingly, incomprehensibly full, of the dispersed and diluted quantum information of everything that ever happened in it, from the first moments after the Big Bang to the final burst of the last black hole. It simply cannot do anything with that information. It cannot organize it. It cannot access it. It cannot convert it into any form of complexity or structure. The maximum entropy state is a state of perfect information dispersal and perfect inaccessibility. This is, in a way, a different kind of ending than the one we might have imagined. The universe does not forget. It disperses. The difference matters to physicists, but for any observer within the universe, the practical result is identical. The past is unrecoverable. We began this journey by mentioning the black hole at the center of our galaxy, Sagittarius A, the 4 million solar mass object whose shadow was first directly imaged in 2022. It is worth returning to it now, at the end of this journey, with fresh perspective. Sagittarius A is a familiar object by now. It is relatively modest by supermassive black hole standards. Millions of solar masses rather than billions. It is currently in a relatively quiet phase of its life, not actively accreting large amounts of material. It is surrounded by a small number of stars in tight orbits, whose precise motions provided some of the strongest evidence for the black hole's existence before we could image it directly. What does Sagittarius A look like in the context of what we have discussed tonight? It is an object in the early stage of a career that will last for an almost incomprehensible span of time. It formed, presumably, through the early accumulation of mass in the young Milky Way, growing through mergers and accretion across the history of the galaxy. It is currently a middle-aged object by the standards of its own eventual lifetime. The Hawking radiation it emits right now is at a temperature so close to absolute zero, roughly 3 times 10 to the power of negative 14 degrees Kelvin, that it is not only unmeasurable, but completely swamped by the cosmic microwave background, which is itself cold, but still vastly hotter than Sagittarius A's Hawking temperature. In the far future, Sagittarius A will grow or shrink depending on the balance between what it accretes and what it loses. For the foreseeable future, it will continue growing as the Milky Way merges with the Andromeda Galaxy, a collision that is expected to begin in roughly 4 billion years. It will likely merge with Andromeda's central black hole and emerge as a larger, combined object. That merger will produce ripples in space-time, gravitational waves, propagating outward across the universe, announcing the event to any instruments sensitive enough to detect them. Eventually, as the stellar era winds down and the galaxy evolves through its long late stages, the accretion rate onto the central black hole will decline. The gas and dust that currently provide fuel will be exhausted. Sagittarius A will grow quieter, darker, and more isolated. And then, over timescales that dwarf the entire history of the universe so far, it will begin to lose mass to Hawking radiation. Slowly, almost imperceptibly slowly, but continuously. Whether Sagittarius A will be the last black hole to survive, whether it will be the one we have been contemplating throughout this documentary, depends on what the universe holds beyond our observable horizon and on which black holes manage to grow the largest through the full history of cosmic structure. Sagittarius A is a contender, but likely not the winner. More massive black holes almost certainly exist and will out-survive it. But it is the black hole we know most intimately, and knowing what we now know, it looks different than it did before. It is not merely a dramatic feature of our galaxy's center. It is not merely the backdrop for extraordinary stellar orbits and occasional flares. It is an extraordinarily long-lived object in the early phase of its existence. One that will persist long after everything else we can see has gone dark, evaporating quietly across timescales that make the current age of the universe look like a brief announcement before the main event. The story we have told tonight is not complete. No honest account of the universe's far future can be complete, because the physics required to fill in the details, particularly the physics of quantum gravity and the resolution of the black hole information paradox, is not yet in our possession. To understand the final moments of black hole evaporation in full detail, we need a theory that successfully merges quantum mechanics and general relativity. This has been the central challenge of fundamental physics for more than half a century. We have two extraordinary theories. Quantum field theory, which describes the behavior of matter and energy at the smallest scales with breathtaking precision, and general relativity, which describes the geometry of space-time and the nature of gravity with comparable precision at larger scales. And these two theories are fundamentally incompatible in the regimes where both are relevant. Regimes that include the interior of black holes and the conditions of the very early universe. String theory is the most developed candidate for a theory of quantum gravity, and it has made significant contributions to the information paradox debate, particularly through the AD-SCFT correspondence, a mathematical equivalence between certain theories of gravity in a particular space-time geometry and quantum field theories without gravity on the boundary of that geometry. This correspondence has been used as a formal tool to argue that information is preserved in black hole evaporation because the equivalent calculation in the boundary quantum field theory can be done without violating information conservation. But string theory in its current form makes it difficult to derive specific, testable predictions for ordinary experiments, and the question of whether the ADS-CFT correspondence applies to the kind of black holes that exist in our universe, which does not have the special geometry required for the correspondence to hold exactly, is still debated. Loop quantum gravity is another approach, one that attempts to quantize the geometry of spacetime directly, without the additional structures that string theory introduces. It makes different predictions about the final moments of black hole evaporation. In some versions, predicting that a black hole does not evaporate completely, but instead leaves a stable, Planck-scale remnant, and its implications for the information paradox are actively being worked out. What both approaches agree on is that the semi-classical physics that describes most of a black hole's lifetime breaks down in the final moments, and that a complete understanding of those moments requires the missing theory. The last fraction of a second of the last black hole's existence is, in a very precise sense, the regime where our current physics ends and the unknown begins. This is not a confession of failure. It is a description of the frontier. Physics has always had a frontier, a boundary between what is understood and what is not. What makes the frontier associated with the last black hole remarkable is its location in time. The unknown physics is needed not to describe some experiment we can conduct in the next decade, but to describe an event that will not occur for a time so distant it makes the current age of the universe look like a single tick of a cosmic clock. Nevertheless, the questions are real. The need for a quantum theory of gravity is real, and working toward it now. While we still have the complex, energy-rich, organized universe that allows for research and discovery, is one of the most significant intellectual endeavors humanity has ever undertaken. The story of the last black hole is ultimately a story about endings. And endings, for beings who experience time as we do, carry a weight that purely Vermschlakischen can only partly convey. There is something deeply strange about contemplating an ending so remote and so complete. The universe as we know it, rich, complex, luminous, alive with possibility, will eventually give way to something that is the universe's own negative, a maximally disordered state in which none of the organized structures that allow for experience of any kind persist. What should we make of this? The question is not a scientific one. Science describes what happens. What we should make of it is a question for each person who encounters the knowledge. But a few observations are worth offering. The first is that the existence of an ending does not diminish what precedes it. The stars that burn for billions of years before collapsing into stellar remnants do not burn less brightly because they eventually go out. The galaxies that form and evolve and eventually disperse do not lose their reality because they are not eternal. And human experience, curiosity, love, and understanding, whatever they are, do not lose their significance because the universe in which they occur will, after an almost incomprehensible span of time, become too simple and cold to support them. The second observation is about scale. We began this evening at the scale of a single black hole at the center of a galaxy. We have traveled to the scale of the entire universe across its full timeline. And what emerges from that journey is not a sense of smallness, exactly, but rather a sense of precision. A sense that the specific, unlikely, early moment we occupy has a character that is unique to this era, and that the tools for understanding the full arc of cosmic history exist only in this brief window. The universe in its final state is simple. The universe in our era is complex. Complexity, wherever it exists, is where the interesting things happen, where questions can be asked, where answers can be found, where understanding can emerge and persist for some span of time. We are in that window. The third observation is that the ending, however remote and however dark, is coherent. It is not random. It follows from physics. The same laws that govern the fall of an apple, the orbit of a planet, the burning of a star, the collapse of a supernova, and the evaporation of a black hole also govern the final state of the universe. The universe does not end arbitrarily. It ends as the logical consequence of the same rules that made it what it is today. There is something in this worth holding on to. The universe is, in the deepest sense, consistent. It does not contradict itself. The end is contained in the beginning, not as fate, but as the natural consequence of persistent, universal laws operating without exception from the first fraction of a second after the Big Bang to the last particle of Hawking radiation dispersing in the final dark. Let us return one final time to the object at the center of our story, the last black hole, whatever it is, wherever it sits in the universe. However many solar masses it has accumulated over its extraordinary lifetime, it floats in a universe that has become, by every measure we know how to apply, completely empty. There are no other organized objects, no other sources of light, no other gravitational wells of any significance within any distance that is relevant on the time scale of its evaporation. It has a mass, it has a spin, it may have a residual electrical charge, though that is likely to have been neutralized over its long history. It has an event horizon, a sphere in space beyond which nothing escapes, whose radius, for an object this massive, might span distances we would consider enormous on human scales, though modest by galactic standards. Around that event horizon, the universe is not quite empty. The Hawking radiation field, the quantum fluctuations of spacetime at the horizon that produce the faint, steady drain of mass, is present. The temperature at the horizon is almost unimaginably low, but it is above zero, and the mass is declining, not noticeably, not on any time scale that would register on any instrument or observational approach we have. But by the unforgiving arithmetic of Hawking's formula, the mass is declining. Each quantum emission takes some tiny fraction of the black hole's mass and sends it outward as a particle or a photon, expanding away from the horizon at the speed of light, carrying energy into the surrounding void. The black hole does not object to this process. It has no experience of it. It simply continues to exist as it has for an incomprehensible span of time, defined by 3 numbers and surrounded by the undisturbed geometry of space-time. Outside the event horizon, at large distances, the space-time is essentially flat. The black hole's gravity, though enormously strong near the horizon, falls off with distance, and in an expanding universe, the distances relevant to the cosmic background have grown to the point where the black hole's gravity is negligible. On the scale of the universe itself, the black hole is alone in a way that surpasses any ordinary meaning of aloneness, and still it evaporates. For an era, for multiple eras, for spans of time that dwarf every other time scale in our story. And then, gradually, the temperature begins to rise. The mass begins to fall more quickly. The horizon shrinks, the radiation brightens. The final phase approaches, carrying with it the last encoded information of the universe's entire history, in correlations too subtle and too dispersed ever to be read. And then, the burst, the final intense emission, the last moment of Hawking radiation, the event horizon contracting to nothing, the singularity, whatever it truly is, no longer shielded, no longer separated from the rest of the universe by an unbreakable boundary. And then, spacetime without a black hole. For the first time in the universe's history, after all the epochs, all the eras, all the incomprehensible span of time from the Big Bang to this moment, there are no black holes anywhere. The universe is empty in a new way. Not the emptiness between galaxies. Not the emptiness after the stars go dark, but an emptiness that is complete in a way it has never been before. A universe in which no region of space-time is severed from any other, where no event horizon separates any interior from any exterior, where the geometry of space, though curved by the residual effects of the expansion, is nowhere so severely distorted that light cannot travel from any point to any other. It is a universe without secrets. Everything that was hidden behind event horizons across the full history of cosmic time has now been released, encoded in the thermal noise of dispersed radiation, inaccessible but present, and what remains is the expanding void, carrying within it the quantum memory of everything that ever happened, and doing nothing with it. We have followed the universe from the black holes that exist today to the last one that will ever exist. We have traced the Hawking evaporation that slowly, inevitably, drains each one of its mass. We have confronted the information paradox and the uncertain physics of the final moments. We have contemplated what remains after the last black hole is gone. And at the end of all of this, a question remains that physics cannot answer. Not because physics is insufficient. It has been extraordinary in what it has revealed, but because this particular question falls outside the domain of what empirical science investigates. The question is, why does physics work the same way at the very end as at the very beginning? Why is the same set of laws that govern the first fraction of a second after the Big Bang still operative, when the last black hole completes its evaporation? Why does the universe have consistent rules at all, rather than changing them arbitrarily? Why is there a Hawking temperature, rather than black holes simply lasting forever? Why does information, if it is preserved, trace a curve that peaks and then declines, rather than doing something else entirely? These are not questions that have obvious answers. They are not even questions that have obvious frameworks in which to look for answers. They are the kind of questions that arise when physics has been followed to its furthest reachable limit, and the mind naturally turns to ask about the frame that contains it. The universe, as we have found it tonight, is a place governed by deep regularities that operate without exception across incomprehensible spans of time. Those regularities produce extraordinary things: stars, planets, chemistry, biology, minds capable of contemplating the timescale of black hole evaporation. And they also produce the eventual dissolution of all of those things into a dark, equilibrated void. Whether that arc from complexity to simplicity, from richness to emptiness, from the golden age of stars to the final evaporation of the last black hole, has any meaning beyond its physical description, is a question that science observes without answering. What science does tell us is that the arc is real, it is coherent, It is governed by laws that are, within their domain, complete. And those laws, when followed with enough patience and enough curiosity, reveal a universe that is far more astonishing than it first appears, not just in its current state of galaxies and stars and life, but in its full duration from a hot, dense beginning to the last whisper of hawking radiation from the last black hole that will ever exist. We are here in the early moments of that story. The night sky above us contains billions of galaxies, each one a galaxy of stars. Each star, a fusion reactor burning for millions or billions of years. The black hole at the center of our galaxy is one of billions, doing what black holes do, persisting with a patience that makes our entire civilization look like a momentary flicker. And in the unimaginably distant future, long after every star has gone dark and every civilization has ended, and every remnant of the stellar era has dissolved, one object, the last one, the most massive, the final survivor, will still be there, evaporating, cooling, radiating the last of its mass into the surrounding dark until the horizon closes, and the universe begins its longest, darkest, and most complete era of silence. We do not know which black hole will be the last. We do not know exactly when its final evaporation will occur. We do not know, with complete certainty, what happens in its final moments or what, if anything, it leaves behind. But we know it will happen. And that knowledge, the capacity to follow the laws of physics from the current moment to the end of all organized structure in the universe, is itself one of the most remarkable products of this brief, luminous era in which we find ourselves. The universe gave rise to minds that could understand it. And those minds, looking outward and forward, found that even the most permanent-seeming structures in the cosmos are temporary. Even the black holes that outlast everything else are not eternal. Even the last one will end. What persists, as far as we can tell, is the geometry of spacetime itself, expanding, cooling, fluctuating at the quantum level, carrying the dispersed information of everything that ever happened, and doing so forever. The universe, in the end, is not nothing. It is the memory of everything, dispersed beyond recovery, persistent beyond all imagination, still here,